The instantaneous current and the phase relation between current and voltage of an LCR circuit can be determined using two methods, namely the phasor diagram solution and the analytical solution. In this module, we shall study the phasor diagram solution. Consider a circuit comprising of a resistor of resistance R, a capacitor of capacitance C, and an inductor of inductance L connected in series to an AC source with voltage V equal to Vm sin omega t. Here, Vm is the maximum applied AC voltage and omega is its angular frequency. As per the convention being used, subscript m denotes maximum value or amplitude of the quantity being considered. In the circuit, we see that the applied AC voltage V is the instantaneous voltage across the circuit. At any instant, the charge on the capacitor is Q. The current in the circuit is I, and di by dt represents the rate of change of current in the circuit. Instantaneous voltage across the capacitor is equal to Q by C. The voltage across the resistor is IR, and the induced EMF across the inductor is minus LdI by dt. The negative sign here denotes the direction of the induced current through the conductor according to Lenz's law. Applying Kirchhoff's loop rule to this circuit, we get Q by C plus IR plus LdI by dt minus V equal to 0. Let this be equation 1. Since V is equal to Vm sin omega t, we get Q by C plus IR plus LdI by dt is equal to Vm sin omega t. As we know that the three circuit elements are in series, thus the current I through them is the same. Thus, we have I is equal to Im sin omega t plus phi, where Im is the amplitude of the AC current in the circuit, omega is the angular frequency, and phi is the phase difference. Now we will use the phasor approach to find the expression for the instantaneous current I. Let the instantaneous voltages or potential differences across the three circuit components be VL for the inductor, VR for the resistor, and VC for the capacitor. We know that the voltage in the inductor leads the current in the circuit in phase by pi by 2 in a pure inductive circuit. The phasor diagram for the inductor shows the phase relation between V and I in the inductor. Conversely, the voltage in the capacitor lags the current in the circuit in phase by pi by 2 in a purely capacitive circuit. The phasor diagram for the capacitor shows the phase relation between V and I in the capacitor. The amplitude of the voltage across the resistor is Vrm equal to Im into R. The amplitude of the voltage across the inductor is VLm equal to Im into XL, where XL is the inductive reactance of the inductor. We know that XL is equal to omega L. The amplitude of the voltage across the capacitor is Vcm equal to Im into Xc, where Xc is the capacitive reactance of the capacitor. We know that Xc is equal to 1 by omega c. The instantaneous total voltage V in the circuit is equal to the algebraic sum of the instantaneous potential differences across the resistor, capacitor, and inductor represented as VL, VC, and VR respectively. And this can be vectorially represented as sum of the phasors VL, VC, and VR, which can be calculated as follows. The amplitudes of the potentials across the capacitor and inductor are VC and VLM respectively, and are at a phase difference of pi/2 from that across the resistor, that is VRM, and they lie on the same line on the phasor diagram. Hence, the phasors VL and VC lie on a line perpendicular to VR, but in directions opposite to each other. Considering the directions of VC and VL on the phasor diagram, we can obtain a single phasor for VC plus VL with the magnitude of VCM minus VLM. Here, we assume that the capacitive reactance XC is greater than the inductive reactance XL, and hence we have VCM greater than VLM. The phasor with the magnitude VCM minus VLM is at right angles to the phasor with the magnitude VRM. The amplitude of applied AC voltage VM can be calculated by using Pythagorean theorem on the simplified phasor diagram. Substituting the values, we see that Vm square is equal to Vrm square plus VCM minus VLM square. Using the values of VRM, VCM and VLM, we get Vm square is equal to IMR square plus IMXC minus IMXL square. Vm square is equal to Im square into R square plus XC minus XL square. Let this be equation 2. Or we have Vm equal to Im into under root R square plus XC minus XL square. Now, we have Im equal to Vm by under root R square plus XC minus XL square, which is equal to Vm by Z. Let this be equation 3. Here, Z is the impedance of the LCR series AC circuit, which is analogous to resistance in a DC circuit, and is equal to under root R square plus XC minus XL square. Let this be equation 4. The impedance equation can also be written as Z square is equal to R square plus XC minus XL square. This equation represents a right-angled triangle as per Pythagoras theorem. This triangle is called the impedance diagram. In an LCR series AC circuit, the phase difference phi existing between the voltage and the current can be determined by using the impedance diagram. In the impedance diagram, the hypotenuse gives the impedance Z. Here, we observe that tan phi is equal to XC minus XL by R. Let this be equation 5. Phase difference phi is equal to tan inverse of XC minus XL by R. Thus, the current flowing through the LCR series AC circuit can be given as I equal to Im sin omega t plus phi, where Im is given by equation 3 and the phase difference phi can be calculated from the equation 5. Hence, we have obtained information of all the entities we desired using the phasor approach to the LCR circuit. Consider a circuit comprising of a resistor of resistance R, a capacitor of capacitance C, and an inductor of inductance L connected in series to an AC source, which applies a voltage V equal to Vm sin omega t at any instant of time t. Here, AC voltage V is the instantaneous voltage existing in the circuit. At any instant of time, the charge on the capacitor is Q. The current in the circuit is I, and di by dt represents the rate of change of current in the circuit. Instantaneous voltage across the capacitor is equal to Q by C. The voltage across the resistor is IR, and the induced EMF across the inductor is minus LdI by dt. The negative sign here signifies the direction of the induced current according to Lenz's law. Applying Kirchhoff's loop rule to this circuit, we get Q by C plus IR plus LdI by dt minus V equal to 0. Let this be equation 1. Since V is equal to Vm sin omega t, we get Q by C plus IR plus LdI by dt is equal to Vm sin omega t. We know that the instantaneous current I is equal to dq by dt. Hence, we get Q by C plus R dq by dt plus LD square Q by dt square is equal to Vm sin omega t. Let this be equation 2. As the three circuit elements, the resistor, the capacitor, and the inductor are in series, the current through them is same in amplitude as well as in phase. Let us now assume a solution for the equation 2 as Q is equal to Qm sin omega t plus theta, where Qm and theta are constants. Qm is the maximum charge on the capacitor. Then, we have I equal to dq by dt is equal to Qm omega cos omega t plus theta. Let this be equation 3. Similarly, we have d square q by dt square equal to minus Qm omega square sin omega t plus theta. Substituting these values in equation 2, we get Qm sin omega t plus theta by C plus R Qm omega cos omega t plus theta minus LQm omega square sin omega t plus theta equal to Vm sin omega t. Taking omega Qm common in the left-hand side of the equation and rewriting the expression, we get omega Qm into sin omega t plus theta by omega c plus R cos omega t plus theta minus omega L sin omega t plus theta is equal to Vm sin omega t. Since capacitive reactance Xc is 1 by omega c and inductive reactance XL is equal to omega L, we can write the above relation as omega Qm into Xc sin omega t plus theta plus R cos omega t plus theta minus XL sin omega t plus theta equal to Vm sin omega t. Or omega Qm into R cos omega t plus theta plus Xc minus XL into sin omega t plus theta equal to Vm sin omega t. Let this be equation 4. Similar to resistance in a DC circuit, we introduce a quantity impedance in AC circuits, denoted by Z. Here, Z is the impedance of the LCR series AC circuit and is expressed as Z is equal to under root R square plus XC minus XL square. In equation 4, multiplying and dividing the left-hand side by the impedance of the circuit Z, we get the equation 5. If sin phi is the difference of capacitive and inductive reactance divided by the circuit impedance, that is, sin phi is equal to XC minus XL by Z, where phi is the phase difference between the instantaneous current and the voltage. Then, cos phi gives the relation between the resistance with the circuit impedance, that is, cos phi is equal to R by Z. Now, sin phi by cos phi will be equal to tan phi, which will be equal to XC minus XL by R. If the relations between Z, R, and XC minus XL are represented through a diagram, they form a right-angled triangle as shown. This is called the impedance diagram. From the impedance diagram also, we observe that tan phi is equal to XC minus XL by R. Hence, we get the same relation for phi as was obtained through the phasor approach that we learned earlier. Substituting the values of cos phi and sin phi in equation 5, we get Qm omega Z cos phi cos omega t plus theta plus sin phi sin omega t plus theta is equal to Vm sin omega t. This can now be written as Qm omega Z cos omega t plus theta minus phi equal to Vm sin omega t. Let this be equation 6. Here, we have used the trigonometric transformations identity cos A cos B plus sin A sin B is equal to cos of A minus B. Comparing the values on both the sides of equation 6, we get Vm equal to Qm omega Z, which is equal to Imz. Therefore, maximum voltage in the LCR circuit, Vm, is equal to maximum current in the circuit, Im, into impedance of the circuit Z. Also, as cos omega t minus pi by 2 is equal to sin omega t, we have theta minus phi is equal to minus pi by 2. From equation 3, for the instantaneous current I is equal to Qm omega cos omega t plus theta. Since Im is equal to Qm omega, we get I equal to Im cos omega t plus theta. Since theta minus phi equal to minus pi by 2, we have theta is equal to phi minus pi by 2. We can simplify the above equation as I equal to Im cos omega t plus phi minus pi by 2. Thus, we have the instantaneous current in an LCR circuit. I is equal to maximum current in the circuit, Im into sin omega t plus phi. To know the maximum value of the current in LCR circuit, we use the equation for maximum current Vm is equal to Imz. Substituting the value of the impedance Z, we get Im equal to Vm by under root of R square plus XC minus XL square. Thus, the relations finally obtained from the analytical approach towards computing the unknowns in the LCR circuit are the same as computed through the phasor approach. This analytical approach can be regarded as a pure algebraic approach, whereas phasor approach is more of a geometrical one. Resonance is a phenomenon observed in systems that tend to oscillate at some fixed frequency. This frequency is called the natural frequency of the system. If the system oscillates at its natural frequency under the influence of an external periodic force, then the amplitude of the oscillations is noticeably larger than those at other frequencies. Consider 4 pendulums P, Q, R, and S suspended from a rigid support as shown. The lengths of the pendulums P and Q are equal. The lengths of the other 2 pendulums R and S are different from that of P and Q. Initially, all the pendulums are at rest and hence do not oscillate. When the pendulum P is made to oscillate, after a certain period of time, all the other 3 pendulums oscillate as well. Here, the oscillation is due to an external force, which is from the pendulum P. Out of the 3 pendulums Q, R and S, the length of pendulum Q is equal to that of pendulum P. Hence, the natural frequencies of these 2 pendulums are equal, and this gives rise to the situation where the pendulum Q oscillates with increasing amplitude due to resonance. This is an example of resonance in mechanical systems. Similarly, the phenomenon of resonance can also be observed in electrical systems. Let us now study about the phenomenon of resonance in an LCR series circuit. We have seen that at any instant t, the applied AC voltage is represented as V equal to Vm sin omega t, where Vm is the amplitude of the AC voltage and omega is its angular frequency. At the same instant, the current in the circuit is given as I equal to Im sin omega t plus phi, where phi is the phase difference between the AC voltage and the current. The phase difference, phi, can be calculated by the expression tan phi equal to xc minus xl by R, where xc is the capacitive reactance, xl is the inductive reactance, and R is the resistance. We know that the amplitude of current Im in an LCR circuit is given by Vm by Z, where Z is the impedance of the circuit. In terms of capacitive reactance Xc and inductive reactance XL, we have Z is equal to square root of R square plus Xc minus XL square. Substituting the value of Z, we get Im as Vm by square root of R square plus Xc minus XL square. Let this be equation 1. We also know that Xc is equal to 1 by omega c and XL is equal to omega L. For resonance in an LCR series circuit, the amplitude of the current in the circuit should be the maximum. For this, the necessary condition is Xc should be equal to XL. Substituting the values of Xc and XL in the expression, which is the condition for resonance, we get 1 by omega c equal to omega L, or omega square equal to 1 by LC. On further simplification, we get omega is equal to 1 by square root LC. Let this be equation 2. Let us now call this angular frequency as omega naught. This frequency is also referred to as the resonant frequency of the circuit. We observe that as omega is varied, the value of current changes and is maximum when the value of omega is equal to omega naught, such that XC is equal to XL. As the impedance Z of the circuit minimizes and becomes equal to R. This is the condition for resonance. Now, equation 1 can be written as Im is equal to Vm by R. Thus, we observe that when the angular frequency omega of applied AC voltage becomes equal to the resonant frequency omega naught, the amplitude of current Im reaches its maximum. Resonance is possible only in a circuit which has both capacitive and inductive components, as the condition Xc is equal to XL needs to be satisfied. Thus, resonance can be observed in a series LCR circuit or in a series LC circuit, and cannot be observed in RC or RL circuits. This can also be observed from the graph of Im plotted against omega, with Im on the y-axis and omega on the x-axis. Here is a sample graph for the amplitude of current Im versus angular frequency omega, plotted for the values L is equal to 1 millihenry, C is equal to 1 nanofarad of an LCR circuit with two different values of resistance R. The first plot is for the value R equal to 100 ohm, and the second one for R equal to 200 ohm. The amplitude of the source voltage Vm is taken equal to 100 volt. For the given set of values of L and C, we find that the value of omega naught is equal to 10 power 6 radian per second, which is equal to 1 mega radian per second. From the graph, we see that the amplitude of the current in an LCR circuit is the maximum when the angular frequency omega naught is equal to 1 by root LC for either of the resistance values. For other values of the frequency, the amplitude of the current is less than that at the resonant frequency. We also observe that except for the case of resonance, for every single value of Im, there are two values of angular frequency omega 1 and omega 2 respectively, one lesser and one greater than omega naught, which lie symmetrically on either side of omega naught. Let us consider the specific case of the frequency at which the amplitude of the current is 1 by root 2 times the maximum value of the amplitude of current, Imax, at natural frequency. Let the corresponding angular frequencies be omega 1 and omega 2. From the graph, we have omega 1 is equal to omega naught minus delta omega, and omega 2 is equal to omega naught plus delta omega, where delta omega is the difference between omega naught and omega 1 or omega 2. Hence, the difference between omega 2 and omega 1 is equal to 2 delta omega. This is known as the bandwidth of the circuit. The ratio of omega naught to 2 delta omega is a measure of the sharpness of the resonance. A larger ratio indicates a sharper resonance. Let us now calculate the value of delta omega using equation 1 for the angular frequency omega 2. Since amplitude of current is 1 by root 2 times the maximum current at resonance, we get Imax by root 2 is equal to Vm by R into root 2, On simplifying, we get omega 2L minus 1 by omega 2C is equal to R. Substituting the value of omega 2 is equal to omega naught plus delta omega in this equation and simplifying, we get equation 3 as shown. Using binomial approximation on the expression 1 by 1 plus delta omega by omega naught in equation 3, we get equation 4 as shown. On simplifying this equation, we get delta omega is equal to R by 2L. Using the value of delta omega obtained, the sharpness of the resonance, omega naught by 2 delta omega, can now be written as equal to omega naught L by R. This is also referred to as the quality factor, Q, of the circuit. Since omega naught L is equal to 1 by omega naught C for resonance, we can also write equation 4 as Q is equal to 1 by omega naught CR. Let this be equation 5. From the expression omega naught by 2 delta omega is equal to omega naught L by R, and the expression Q is equal to omega naught L by R, we get the bandwidth of the circuit as 2 delta omega is equal to omega naught by Q as shown. This indicates that a higher value of the quality factor leads to a sharper resonance as the bandwidth decreases. One of the important applications of LCR series resonance is in the tuning of radio and TV receivers. The circuit diagram shows a typical arrangement consisting of an LCR series circuit used for receiving signals. In this arrangement, the antenna receives various signals and feeds it to the input. This induces a signal at the coil of inductance L in the LCR series circuit. While tuning, the capacitance in the circuit is varied, such that the resonant frequency of the circuit becomes nearly equal to that of frequency of the radio signal being fed at the input for a particular value of the capacitance. Now, the amplitude of current in the circuit becomes the maximum, and we get a high quality factor as delta omega is the minimum at resonance. In this manner, the LCR series circuit can be used to tune into a large number of frequencies of signals in radios and televisions. We observe that when the resonance is less sharp, the selectivity of the circuit will be lesser, as there will be a large range of delta omega frequencies for which the LCR series circuit will be close to resonance. We also observe that for a large quality factor, we should have large value of L or a low value of R for the expression Q is equal to omega naught L by R.